Hello everyone, I'm Shweta Shinde and today I'll be presenting our work, BesFS. TEs are a hardware feature that allow us to launch secure applications in an environment called a secure enclave. They provide a guarantee that all the data and computation happening inside an enclave will be protected from a potentially malicious operating system or a hypervisor. There have been many hardwares which support such TEE features, including Intel's SGX. As much as TEEs are useful for protecting applications, they leave a caveat wherein if the application ever uses an untrusted interface with the operating system, such as a system call, it is exposed to a severe threat of attacks, typically called as Iago attacks. What happens here is an application can get compromised by using untrusted outputs provided by the operating system. In fact, when we looked at existing frameworks for TEEs, we found evidence that popular frameworks such as Google's ASLO and Intel's SGX SDK do not filter out the attacks from the operating system. Concurrently, several other researchers identified similar threats. On the other hand, there are very few solutions to this problem. Some of them include limiting the surface of attack by exposing as small an interface as possible, employing rigorous sanitization to check whether the outputs are malicious before consuming by the application, and then automating these checks using compilers. As much as these solutions are useful, they are not complete. They do not give any guarantee that the application will always be able to detect attacks from the operating system via this vulnerable interface. In this work, we asked the question, is there a way to formally verify that the interface is safe against all attacks launched by the OS via this interface? There are two main steps in such an approach. The first one is, what is the safe specification? What is the interface legitimately allowed to do? Let's say in an open system call, what are the inputs and outputs to the OS which are correct and do not mount an attack? And then how to check whether an implementation of this interface indeed abides to the specification. There are several works in file systems and system call APIs which take this approach. However, none of the previous works have included the scenario where the operating system itself is malicious. This opens up a very complicated verification problem because there are simply too many states in which the OS is malicious, and the task here is to identify the smallest possible state which is safe. When we began looking at this problem, we looked at two possible solutions, possible ways of framing this problem. One similar theme was that how do we scale our specification to a very large interface? Typically, the system call interface includes 300 APIs. Simply writing down a specification for these APIs is a large task. The second approach that we looked at was verifying an existing implementation, be it of a libc library or a file system implemented correctly, such as ext4. However, verifying an existing implementation is also a large task because the code base is very large. Instead, what we settled on was writing a very small subset of specification which we deem as safe. What does this safe specification entail? In this work, we call it as the BesFS interface. We have specified an interface for a file system. The way we have designed this is keeping scalability in mind. Right? So what the specification includes is a core subset of 15 APIs, which are frequently used to interact with files via system calls, such as open, read, write, and close. Along with these 15 core APIs and the specification, we also carefully design it in such a way that our specification allows us to execute a sequence of these APIs. And the specification guarantees that any arbitrary sequence of these APIs abides by the safety property. With this addition to the specification, we are able to chain multiple calls and reason about a composition of these interfaces. For instance, our core interface includes write and fstack call. Composing these two together, we can prove the safety of another call called frun. In fact, with this composition built into our specification, we were able to scale our safety properties from 15 core APIs to 22 additional APIs. With this in mind, let's take a look at what exactly are the details of the BesFS interface. There are two major parts to BesFS interface. The first one is our state safety properties. This is a list of 5 properties that our file system should always abide by. One such example is that all the paths for files and directories should always be unique. There are 4 other properties that if you're interested in, you can take a look at the paper, right? The main part of a state safety property is that they should hold true for all states of an enclave when it's trying to use this interface. However, this is not sufficient. There are interface-specific properties. For example, if the application is trying to invoke a closed system call, we also specify what preconditions the enclave should satisfy before using this interface, and if the OS returns a value, what are the post conditions that should be satisfied before the application can use the outputs of this call. Thus, the state transition properties allow us to identify whether we are in a good state or not. And the transition property tells us, are we allowed to do a call, and are we allowed to consume the results of this call? Put together, what we have are 2 main theorems that we proved in a theorem prover. The first theorem says that if we start in a good state, which satisfies all the state properties, and it also satisfies a precondition for a call, if our system allows the call to happen correctly, then the post conditions are always satisfied, and the new state that is reached is also a good state. So you could think of this as the base case of an induction proof, which allows us to take one step in the state machine. And the second theorem says that you can sequentially compose these calls such that if you start in a good state, the specification ensures that you always reach a good state after n calls. So you could look at this as the induction step of the proof. With these 2 proofs over our specification, we are sure that our specification allows us to compose multiple calls. However, the next question was that does there exist a real implementation which can satisfy all the specification properties? To do this, we went ahead and we implemented a file system check in a higher level language called Galena. Our theorem prover called Coq was able to understand this implementation, and we ended up using a lot of data structures such as files and directory layouts and so on to keep track of the file system state. And eventually, we proved a theorem that our implementation in Galena indeed satisfies all the specification properties that we wanted in our BesFS interface. So at the end of this, what we had was we were able to prove that indeed there exists an implementation which can satisfy all the BesFS interface properties. With this implementation in hand, we were curious to know whether BesFS can deliver on 4 main criteria. To quickly summarize, the amount of code that we had to add, including the specification, the implementation, and the proof, was around 5,000 lines of code in a theorem prover called Coq. When we did a hand translation of our implementation to C, it turned out to be around 1,500 lines of C code. In terms of expressiveness, as I said earlier, we started with 15 core APIs, and we were able to synthesize or compose 22 additional APIs, which we were able to prove was safe. In terms of compatibility, we tested around 31 applications, and we found out there were around 2 million instances of API invocations, and out of that, only 8 we were not able to support. In terms of performance, nothing surprising. CPU-intensive benchmarks did not see a lot of overheads, whereas all IO-intensive benchmarks, which did very frequent usage of read-write APIs, saw around 4 to 5x of slowdown. The most interesting part of the verification work were we able to find and eliminate any bugs in real-world implementations. So when we tested our proven implementation against existing implementations, such as in the Intel SGX SDK, in Panoply, which is another system which allows applications to do system calls for files, we found out several instances of either low-level bugs, such as stack corruption due to large sizes, which were not checked when making copies inside an enclave, wrong checks over error codes, and in fact, because we had specification, we were also able to identify bugs in the implementation of our own code. If you're interested in the code, please go ahead and take a look at our webpage. Thank you for your time.